When people hear about cryptocurrency, it's easy to picture literal money living inside a computer, glowing coins locked in a high-tech digital vault. But digital money actually functions as a system of permission. When you swipe a credit card to buy a coffee, your payment terminal sends a signal to a central bank's server. That server checks your account, verifies the funds, and sends back an approval checkmark. This system places a single central authority in charge of the ultimate ledger of truth. They have the power to approve transactions, freeze accounts, or decide which history is valid. This raises a difficult question. How could a group of strangers coordinate a secure currency if they refuse to use a central gatekeeper? Building such a system is an exercise in structural design. The goal is to build a network where the laws of mathematics replace the need for a bank's oversight. Let's start with a communal list. If you and your friends exchange money frequently, you can simply record every transaction on a public board that everyone can see. If everyone agrees to never settle up in physical cash, the numbers on this ledger become the currency. You simply spend the balances you've accumulated according to the list. The immediate problem is authenticity. If anyone can write on this public board, Bob could add a fraudulent line claiming Alice owes him $100 without her consent. Alice's private key generates a digital signature, a massive 256-bit string of ones and zeros linked to that specific transaction. Altering the payment by a single letter causes the signature to scramble into a completely new, mismatched sequence, making forgery impossible. We have a way to prove who sent the money. However, we are still relying on a central authority to host the master copy of this list and ensure no one tries to spend the same money twice. To remove the host, we distribute the ledger. Every single user in the network maintains their own personal copy of the transaction history. When users broadcast transactions at the exact same time, the network descends into noise. Because signals travel at different speeds, users receive the data in different orders, leading to conflicting versions of the ledger. To organize this, we group pending transactions into discrete blocks before they are added to the history. Each block is passed through a one-way hash function called SHA-256, outputting an unpredictable string of bits. To force consensus, users guess random numbers and rerun this function until they find a specific input that produces an output beginning with a long row of zeros. This is a brute force search that requires massive amounts of computational trial and error. By making it difficult to validate a block, it becomes physically impossible for a bad actor to outpace the rest of the network and create a fake history. This creates a simple rule for the network. If you hear two different versions of the ledger, you always trust the one that has the most computational work invested in it. To make the history permanent, we chain these blocks together. Each new block contains the hash output of the preceding block. Changing an old transaction changes its hash, instantly shattering the links to every subsequent block, forcing the fraudster to redo billions of calculations. Because this work is expensive, the system provides an incentive. The first person to find a valid hash and secure a block is rewarded with newly generated currency. This is what we call mining. It is the process of aggregating transactions, performing the computational work to seal them into the ledger, and earning a reward for maintaining the network's security. This self-sustaining loop of verification and reward creates a decentralized network that can defend its own history without a leader. This architecture, using digital signatures, decentralized copies, and brute force computational work, is the blueprint of Bitcoin. The protocol includes built-in constraints. As more computers join the network, the mathematical difficulty automatically adjusts to ensure a new block is added only once every 10 minutes. It also enforces a hard limit of 21 million total coins. Because the block space is limited, users include transaction fees with their payments. Miners prioritize the transactions with the highest fees, pulling them out of the queue and into the next available block. This design prioritizes decentralization over speed. While a centralized network like Visa can handle tens of thousands of transactions per second, the blockchain's slow, deliberate verification is the price of removing the middleman. Bitcoin demonstrated that thousands of strangers can maintain a global economy without a central authority. It replaced human institutions with a ledger protected by the laws of probability.